which becomes multivariate. It's a multivariate version of Ito's lemma. So if you, I believe you know that already. So I just write it here to remind you that there might be some cross variation term. Okay, so it's always better. It's always a better idea to expand everything up to second order, just like what we did in this multivariate Taylor expansion. Just expand everything to up to second order, and then we just forget ignoring this smaller term dt, dt, dwt, something like that. Okay, but do not forget there might be some cross variation term like this one, this cross derivative, etc. And another thing I want to make a comment is that about this Brownian motion with Brownian motion with correlations. So when there is only one Brownian motion, there are no such issues. But when we have multiple assets, multiple randomness, there are always more than one Brownian motions here. So in that case, we usually see this kind of notation: dw1, dw2 equals to rho dt. So just like in a multivariate normal distribution, we have independent case and dependent case. So basically, this is a dependent normal distribution. Okay, dependent Brownian motions. And the correlation coefficient is rho. And once we have correlated Brownian motions, perhaps a good way to simplify or to rewrite everything in terms of independent Brownian motions is we can always do this kind of decomposition. Okay, so that means if we have two correlated Brownian motions, the second Brownian motion can always be decomposed into two parts. The first part is the perfect correlated part, or the parallel part. Okay, rho wt1. Okay, that's a parallel, that's a perfect correlation part. And the second part is the independent part. Okay, or the perpendicular part. Okay, this dzt, that will be a new Brownian motion, a standard Brownian motion that is independent of w1. So usually when we do this calculation, we always prefer independent Brownian motion, because we can do a lot of tricks about when we evaluate an expectation of some normal distributions when the normal distribution is independent. Okay, so we always, actually, at least for me, I always prefer this independent Brownian motion and to do this kind of decomposition. Okay, and but anyway, if you like, you can also use correlated notions. It's the same. It is the same. Okay, but anyway, if you look at the theory relating to asset pricing in the multiple asset market, is all the same. Still, usually our approach is risk neutral pricing. Or sometimes we can do this direct hedging and derive PDEs. And of course, higher dimensional PDEs is a disaster. So basically, we prefer this risk neutral pricing, risk neutral valuations. And in that case, this kind of change of numerical argument can be very useful in many cases. For example, this exchange option or some foreign currency options, this kind of stuff. This change of numerical techniques are really useful sometimes. And we will see that later. But anyhow, it's just the idea is, again, I'll repeat here, is instead of using this domestic currency as our numerator, we can choose a foreign currency as our numerator, or we can choose any tradable asset, and a stock 1, stock 2 as our numerator. It really depends on which kind of numerator can lead to a simpler mathematical expressions for these payoff functions. Okay, and we'll see that in exchange options there. And anyway, we can derive the closed form solution for exchange option. For example, it will look almost like this Black-Scholes formula. Okay, and that's because we later see we derive this whole formula thing based on Black-Scholes ones. And in this cross currency options, when we have a foreign currency and a stock in foreign currencies, okay, stock assets in foreign currencies, we can derive this PDE as we did in our lectures. But also, as I commented last week, this kind of Black-Scholes type PDE will always coincide with the Ito's lemma once we do the Ito's lemma in the right way. Okay, this every term here basically will shows up in the DT term once we apply Ito's lemma. And later in question 4, we will kind of explain why this term is RF minus this number and why this term is this number. Okay, it will be basically we did it by direct hedging in our lectures, but later we'll see we'll also agree with Ito's lemma results. Anyhow, let me just come to the questions. So the first question is about two stocks, and actually, if you look at these expressions closely, you will see these two stocks, both of them are driven by the same Brownian motions. Okay, they are driven by the same Brownian motions, WT. So the similar issues actually we have already seen the similar problems maybe many weeks ago. There we have two stocks, but only one randomness. So there we basically show a way that we can construct a risk-free portfolio, and basically using these two stocks, and basically we can choose two stocks so that we make some smart choices so that we can get rid of this Brownian motion. We can get this Brownian motion cancelled away so that we can result in some risk-free profit. If the numbers are not matched, then basically it will become arbitrage opportunity, which is indeed this case. Okay, so these two stocks have the same Brownian motion. Moreover, they have the same volatility. So basically, all this randomness, all the uncertainties relating to these two stocks are they are exposed to identical risk. Okay, and the stock 1 it grows faster and stock 2 grows slower. Then basically we would like to purchase the faster growing stock 1 and short the slow growing stock 2. So that's our portfolio. Okay, it's a very simple static portfolio. That means we set up the portfolio at the beginning, then we do nothing and we just wait for a while. It just give you a profit. So our strategy is to short the second stock and use all this money we get to purchase the first stock. Okay. So in total, at the beginning, this portfolio setting up this portfolio costs us 0. Okay, costs us nothing because we shall sell some stock and purchase some other stocks. It costs us nothing at the beginning. And if we wait for a while using the explicit formula for geometric Brownian motion thing, you will see this randomness part will become a common factor, and this common factor is always positive because this Brownian motion shows up in the exponential term. Okay, this is the randomness part. It's all no, don't worry, it's just a positive number, and this factor is also positive, and this factor is related to the growth rate of these two stocks. So that you'll see it will always become a positive number of some 1. So that is an arbitrage. Okay, we start from 0, and after a while we get a positive profit. So that's an arbitrage. All right. So the problem is still arranges from this same Brownian motion. Two stocks, same Brownian motion, always a trouble. Okay, so that's question 1. Yeah. So question 2. So question 2 is actually a very interesting question. It's one direction, one part of this fundamental theorem relating to this arbitrage theory. Okay, so it states like this way. So if there is a market and it's a market model, and there exists a risk neutral probability for this model, and then we can claim that there is no arbitrage. Okay, so as long as there is risk-free interest, as long as there is a risk neutral probability, then arbitrage free. All right. So the story is this. So how do we show that? So basically, here we are going to show something does not exist. Okay, there is no arbitrage. So we are going to show something does not exist. So since this guy does not exist, how do we argue for anything? So it's usually very hard to directly to argue something does not exist. So our strategy becomes a proof by contradiction. Okay, our strategy is proof by contradiction. That means we assume this guy exists, and then we can derive some contradicting results. Then we know our assumption at the beginning will be wrong, so that this guy does not exist. Okay, so we assume there is an arbitrage opportunity. Okay, there exists an arbitrage opportunity. So what does that mean? That means we can construct a self-financing portfolio pi t, start with 0, it costs us nothing. Then after some while, it becomes non-negative for sure, and becomes positive with certain positive chance. Okay, so that means we will never be bankruptcy, and we will have some chance to get something. Okay, that's the arbitrage. And we are going to make use of some relations, something implied by this risk neutral probability, of course, to show whether it leads to some contradicting results or not. Okay, so since we have the risk neutral probability, so let's recall what is a risk neutral probability measure. So one of the requirements for a risk neutral probability measure is that for any self-financing portfolio, after we take discount, it should be a martingale under this probability. Okay, so let's call this risk neutral probability by Q. So Q already exists here because it's already provided in the question. So I'm not inventing this Q from nowhere. It's already there. Okay, Q already exists. So I'm just making some claims about this Q. So this claim is pi t over mt is a Q martingale. All right. So this is the requirement for this Q to be a risk neutral probability. Okay. Any self-financing portfolio take discount will become a Q martingale. So that since it's a martingale, so that we know one of the basic properties is that if you compute the future expectation, it will equal to the current value. Okay. So the future expectation is pi t over mt. It equals to the present value, the current value, which is pi 0 over m0, which is 0. Sorry, this is 0. Okay, that's because pi 0 is 0. So this is just a number. There is no randomness here at the beginning, so it's just 0. Okay. So we know under Q word, when we do its expectation, it becomes 0. But if you think about it, it may be very weird to have this kind of relations. That's because pi t is always non-negative, and even more, pi t can be positive. So overall, it's very hard for us to imagine why this guy is 0. Okay, since pi t is always non-negative, mt is always not. Mt is just e to the power rtc, so it's always non-negative. So why pi t over mt is 0, the expectation. So basically, that is indeed where this whole thing will break down. But it also requires some rigorous specification of that. That's because pi t is non-negative on the p word. So what about the q word? Because everything relating in this expectation happens under q word. Okay. So that means so basically we need to make some linkage between this p and q. Okay. So that's what we are going to do next. So what is the relation between p word and q word? Actually, this is one of the assumptions in the definition of risk neutral probability map. And perhaps we do not pay enough attention to that, but it's there. Okay? The requirement for this Q to be a risk neutral probability measure is that it is equivalent to P. Okay? This Q should be equivalent to P. That is not some condition I impose here, it's just some endogenous properties relating to this risk neutral probability measure. Okay? It's just one of the requirements for this Q to be a risk neutral probability. So P and Q, they are equivalent. So what does that mean? So mathematically, okay, true probability P and Q, they are equivalent, is defined in this way. It's just a definition. So for anything, for any event A, PA equals 0 implies QA equals 0, and vice versa. Okay. So what does that mean? So suppose I am a Q person, let's say you are a P person, so your probability, your belief is P probability, and my belief is Q probability. If you are saying this event is not going, it's impossible to happen, then I will agree. Okay? If you think this event will never happen, then I will agree with you. Okay? If I think something is not going to happen, then you will also agree with me. That's the equivalent to me. That's what is equivalency mean. Okay? That's mathematical definition of this P and Q that are equivalent. So basically, you and I will agree on some zero probability things. Okay? As long as you think something is never going to happen, then I will agree, and vice versa. Okay? So that's the definition. So if we apply this definition here, let's try to translate this kind of properties in P word to Q word. Okay? So basically, you think pi t greater or equal to 0 is going to happen. Okay, for sure. Then I will also agree. Why? Because your belief can be translated in this way. So basically, you are saying it is not possible that pi t is smaller than 0. Okay, pi t smaller than 0 has probability 0. Okay, you think something is probability of something is 0, and I will agree. So I will agree that pi t cannot be smaller than 0. So it's always non-negative, greater or equal to 0. And the second statement can be translated in this way as well. Pi t larger than 0 is possible. It's possible. Okay? You think this event is possible, I will also think this event will be possible. Okay? Otherwise, if I think this is possible, then you will agree with me, so that it contradicts with this kind of assumption here. Okay? So that in everything on the P word can be translated into these properties on the Q word. Then we'll be fine that because all the statement is under Q word. Okay? So on the Q word, this number is always non-negative, and there are some chances that this number is positive. Then how come that the expectation of this guy becomes 0? Okay, that's contradiction. That's absurd. Okay, that's contradiction. So basically, that's how we argue that there should be no arbitrage. Since once there exists arbitrage, we can conclude that this guy is 0, but based on this kind of observation, it cannot be 0. It must be positive. So that's a contradiction here. Okay? So that's how we argue that there is no arbitrage. Okay? Yeah.
Why PT can't be negative the Q?
Cannot be negative. Okay. So this is the definition of arbitrage. So on the physical probability, okay, on the physical probability, we can never go bankruptcy. Okay, our portfolio is always greater or equal to 0. It's for sure. Okay, that means pi t on the p word. So you are p person, I'm q person. Okay, you would believe pi t can never be negative, right? Pi t can never be negative. So larger than 0 is for sure. Then basically it cannot be smaller than 0. So you think something is probably with probability 0, and then I will agree. So I will agree that pi t cannot be smaller than 0. So that can be translated in this way. So I also believe that it is for sure that pi t is greater or equal to 0. Okay, and similar argument here. So if this probability can be either positive or 0. So if I think this event pi t is larger than 0, is this probability equal to 0? Okay, that means I think this thing pi t cannot be greater, or pi t larger than 0 is impossible. Then you will also agree. If you agree, then it will be this probability pi t larger than 0. You will think pi t larger than 0 is also 0. That is actually not consistent with this condition here. So this number has to be positive. Yeah. Okay. So any other questions? So let's move on to question 3. Okay. So question 3 is a typical question relating to two stocks, and for this question it's about pricing exchange options. Okay. So the exchange option payoff is this guy. So S2 stock 2 price minus stock 1 price takes positive part. Okay. So if we apply risk neutral valuation formula, it's just this one. Okay. We are going to compute the future expectation of this payoff and take discount on the Q word, on the probability Q. Okay, that's it. And why we really need this kind of change of numerator argument? That's because S2 minus S1. What the hell is that? I have no idea how to compute that. So this trick applies in this way. So it's a Q. So I'm going to bring this common. Well, I'm going to bring this S1t as a common factor. Bring this S1t out. And the remaining will become S2t over S1t minus 1 takes positive part. Right? So it can be, if you multiply S1 inside as a bracket, it leads to the same. Okay. So once we do this kind of simple manipulation, this kind of structure will remind us of this European call option. Okay. When we first see this change of numerator argument for European call option, that's exactly the similar structure. St times something very, very, very nasty. But the good thing is we can always absorb this S1t into this probability measure. That's because this discounted asset price is actually a Q martingale. So once we introduce this change of probability or change of numerator, then it will become S01 expectation of QS1, and these two will be absorbed in this probability QS1. And the remaining is just S2t over S1t minus 1 positive part. Okay? Then you could say, if this S2 over S1 is actually, if we regard this S2 over S1, if we regard this ratio as some new stock price, then this expectation is just the European call price. Okay? If we regard this ratio as some stock, then this stock price minus 1 takes positive part, then basically it's a European call option with strike price 1 and underlying asset, this number. Okay? So that's why so basically that will simplify our calculation. So that's why we have this change of numerator argument. And to make it the linkage more explicit, then basically you see this QS1 and this Q, they are related by this density process. Right? Because this is the martingale and normalization constant. Okay? These two is a martingale, so martingale can be absorbed in this probability, change of probability by introducing this density process. And our problem becomes a European call option. So in order to find what's the value for this European option, then there is only one thing we need to do, which is what is the distribution of this stock price? If you think of this ratio as a stock price, what is the distribution of this random variable? It should be a log normal distribution, but what is the mean, what is the variance, so that we can just plug in everything into the Black-Scholes formulas. Okay, so you see this is why we have this question. So the first part is really about what is this ratio. So this is x. This is this ratio we are interested in, and we are going to find out what is the dynamic of this ratio as xt under this q star. Q star you will see q star later. You will see q star is indeed our qs1. Is this risk neutral probability if we use s1 as our new mirror? Why? Because this xt is just the stock 2 price in terms of stock 1 price. That is, if we use stock 1 price as our unit to measure the price, then xt is the stock 2 price, the price of the second stock. And mt over s1, what is that? This is 1t. So that is, we are using the stock price of the first stock to measure all the price of anything. So yt will be the money market price in terms of stock 1. Right? So these two are just another kind of discounted asset price, but here we are using stock 1 as our mirror to measure the wealth, to measure the price. Okay. So since this xt is actually a stock price, is actually a discounted stock price, then xt will become non-market. That's also explain why in this dynamics there is no dt. There is no dt because xt is essentially the discounted asset price. Under the right risk neutral probability, then it should be a market mirror. So there is no dt term. Okay. So in this question, we are going to pin down this sigma 1, sigma 2. And here this dz1, dz2 is two independent Brownian motions. Okay, two independent Brownian motions. So what do we do here? So before I talk about this solution here, I just want to mention a few things relating to this multi-stock or multi-asset market model. So usually our model will be given in this way. So we have multiple stocks, or you could say multiple risky assets. So each of them follow some SDEs, let's say geometric Brownian motion, and let's say just like our question here, we have two stocks. Each of them are geometric Brownian motion, and they have dw1, dw2, and they have correlation. So I would, at least for me, I would always prefer to rewrite the Brownian motion as some independent part. Okay, that means if we take the first Brownian motion as dz1, then the second Brownian motion can be decomposed into rho times dz1 plus this 1 square root 1 minus rho square times dz2. Okay, it's just a very simple decomposition. It's equivalent. Yeah, they mean the same. Okay, so that's our basic model. And then what I'm going to do is I'm going to introduce a matrix or vector notation. And I'm doing that because I want to give you this idea that everything will be parallel to this univariate case. There's almost no difference. Okay? So let's say this ds1 over s1, ds2 over s2, and put them together as a vector. Okay? This is a vector. This guy, you could think of this as almost like ds over st, dst over st. So basically it stands for the stock return. Okay, almost like the stock return. So this guy equals to mu dt times sigma dzt. So what is mu? Mu is mu1, mu2 is vector. Okay, it's a vector, dt. And sigma dzt. So what is dzt? Dzt is still a vector. dz1t, dz2t. It's a 2 by 1 vector. Okay, this sigma is a matrix. It's a 2 by 2 matrix. Okay, so if you compare this, if you do this matrix multiplication and compare the results with these two standalone equations, we can pin down this 2 by 2 matrix. It's a sigma 1, 0. That's because the first row will become sigma 1 times dz1, 0. So this sigma 1 dz1. Okay, and also the second row is similar. So this is that. So if you forget about this, this vector, this matrix, this vector, then basically if you look at this equation formally, it's indeed the same as the univariate case. Okay, dst over st equal to mu dt plus sigma dzt. Okay, agree? It is the same as the univariate case. Okay, dst over st equal to mu dt plus sigma dzt. So usually our first step to do derivative pricing is to change everything from this p word to q word. Okay, so we know on the q word, the drift term, the drift term will always be R. The expected return of all the tradable assets will be R. So we know that finally the drift term will be R dt plus sigma dZtq. So the difference is that we are changing the drift term from mu to R, and of course the Brownian motion will be changed accordingly. So what is the linkage between dZq and dZ? So that's it. Okay, this is the relation between these two. Okay, you can just plug in this to make sure these two equalize. Then basically that's how we pin down this dZq. And you'll see this number, this factor here. In the univariate case, what we have in this term is mu minus R over sigma. Okay. If you check your lecture notes, in the univariate case, here, this number is mu minus R over sigma. So in the multivariate case, it's just sigma inverse mu minus R. Okay. Formally, it's still the same because it's a 1 over sigma inverse. Okay. It means the same thing. So that's dZq. Okay. So that's dZq. So usually that's the dynamic on the Q. So if we want to do this change of universe thing from Q word to QS one word, that means we are going to use this guy as our LT, right? As our density process LT. Okay. So in the univariate case, what do? We got an LT here. So we want to do some Gassino theorem change of universe. Then what do? We apply to lemma to this DLT. Then we write this DLT over LT as some minus kappa times dZtq. Okay, and the kappa will serve as this drift term that we are going to change. Okay, and in this case, kappa in the multivariate case, kappa will become a vector. The only difference is that kappa will become a vector, and since this dZt, this Brownian motion is a vector, so it only makes sense this kappa is a vector. So it's an inner product in two vectors. So once we do that, we can change this Gassino theorem one more time, so that we can replace this dZtz as a dZtq by this dZtq(s1) plus k kappa dt. And if you combine this dt term together, you will get the true dynamic of these two stocks under this QS probability. Okay, that's our Euro trick. That's our Euro approach. Okay, it's very standard. Very, I guess it's easy to follow, but admit it's very tedious. It takes you a lot of time. So I guess I will come back to this question. And for this question, actually, we do not need to go that far, but we can use some smart observations, and we can do that. So I'll show you this solution here. So the first thing is, again, our decomposition. Okay, we always like independent Brownian motions usually. So we have the first decomposition like that. So we introduce dZ1, dZ2. So for now, everything is on the P. Okay, everything is on the P. So instead of doing change of universe step by step like that, we can first apply to lemma to find out what is the dynamic of this xt on the P word. Okay, we do this into lemma to this ratio, and we can find out the dynamic of this xt under this physical probability P. Okay, on the P word. This is the dynamic. This is the dynamic. And finally, we know ultimately the drift term will vanish once we do some change of probability argument. Okay, we know that. So that we know finally our change of probability, the Brownian motions, the new Brownian motion will be introduced in this way. It's always some drift term plus the old Brownian motion, right? The old Brownian motion plus some drift term will become a new Brownian motion. And then we also shift the probability. So that this dt term, the drift term will eventually be gone. Okay, the drift term will be gone finally. And but we always know that in the Gassino theorem, the volatility term will never change. Okay, we never change the volatility term. Just like here, this sigma is always the same sigma. Okay, volatility never change. So that dynamic on the P word and dynamic on this Q star word will share the same volatility term. Okay, the volatility term will be the same. This is volatility term. Okay, volatility term will not be changed. So that we can just stop here, because that's indeed what we are looking for. Okay. So the smart part of this kind of approach is that actually we do not need to know what is theta, because it is not required in this question. we do not need to write down what is theta here. Okay, as long as you have a way to pin down this number and this number, then we are fine. Okay. So this approach actually cannot help you to pin down theta for now. So you still, I guess, you need to figure out a way to pin down theta if you want to know theta. But for this question, indeed, this is enough. This is enough to pin down this volatility term just by directly applying Ito's lemma to this ratio under P word, and volatility term will not be changed. So it will still be this two. Okay. That's the two. This is the sigma 1, sigma 2 we are looking for. Okay, this volatility term. We can just apply Ito's lemma to this ratio on the P word, and volatility term will not be changed. So it's still the same volatility term. Okay, so that's for dxt. And the second part is really about what is the distribution of xt. So you'll see, if you look at this dxt, so I'll give you a more direct way to write this equation. So still, I'm going to divide xt over here. So dxt becomes sigma dot dz. Okay. Still, I prefer this matrix notation. Okay. This sigma star is a vector. Sigma 1, sigma 2. Okay. It's a vector. This is a vector, and this is also a vector. dz1, dz2 vector. Okay. Vector dot vector. That's the inner product between two vectors. Okay. Inner product. So it means the same thing. It's just maybe simpler in math. But anyway, if you look at this kind of expression and forget about this the nature of their both vectors, then you see dxt is indeed a geometric Bernoulli motion, and there is no drift. Drift term is 0. Okay, there is no dt term, and only dwt term, only Bernoulli motion term. So it's a geometric Bernoulli motion with drift. And moreover, we have this geometric Bernoulli motion formula for this kind of x for this x, which is the drift term minus a half sigma squared t times t minus t plus sigma times zt minus the small t. Okay? So I'm using the formulas for the univariate case. Univariate geometric Bernoulli motion. Okay? Univariate geometric Bernoulli motion. From small t to capital T. Okay? So you see maybe some terms here does not make any sense. So for example, what is sigma times z minus z? So again, this dot, this multiplication should also be interpreted as the inner product. Okay, inner product between two vectors. So this is this part. And what about this square term? What is the square of a vector? It does not make any sense. So here the correct interpretation is the Euclidean norm of this sigma vector, which means, so here this number means sigma 1 star square plus sigma 2 square. Okay? So that's it. Okay? That's the formula for xt. Okay? So if you like, you can always double check, you can always verify by applying Ito's lemma to this function, this complicated one, and to verify that it will indeed lead to this differential form. Okay? It's always a good habit to verify that you solve this SDEs correctly by doing some verification. Apply Ito's lemma to this guy, you can find out dxt equal to this. Okay? So you see this xt can be written as x small t, the current value, times exponential to a normal distribution. Everything here is still a normal distribution, and this term will be the mean, and the volatility term or the variance of this normal distribution comes from this sigma and this Bernoulli motion t minus t sigma. Okay, it will contribute to t minus t, and here will also contribute to some variance. And since there are two Bernoulli motions and two normal distributions, and the good thing is it is independent. Okay, we have two independent Bernoulli motions. So the variance of the summation of these two independent parts is just the summation of the variance of each of them. So that we have this. Okay, this is the variance term, and this is the volatility term. Okay, so basically that's the distribution of xt. It is just a geometric Bernoulli motion. Okay, geometric Bernoulli motion with so equivalently it's like this one, right? There is xt here. So equivalently, this dxt equals to xt times sigma dwt, some wt, some Bernoulli motion. Okay. So this is the equivalent formula for that. So once we know this xt, then if we come back here, so you will see the only thing we need to compute is the expectation of this xt minus 1 exposing part under this q star word, under this probability q star. And then we know xt is geometric Brown motion, then it's just a stock with strike price 1. And the interest rate is 0 because the dynamic of xt, there is no drift. Drift is 0, so the drift rate is 0, and volatility is that sigma, that equivalent sigma. So this expectation will become Black-Scholes formula. This is the initial price, this is strike price, this is the interest rate, and this is the volatility. And of course, you can put time to maturity capital T here. Okay, that's our answer. And if you plug in these Black-Scholes formulas, you will finally get, this one. Okay, just this one. This is the Black-Scholes formula part. And if you do one more step, this is the final result. Okay, it's S2 times ND1 minus S1 times ND2. Okay, so it's just some application of change of numerator and Black-Scholes formula. Okay, that's it. So this kind of change of numerator techniques are really useful when we have multiple stocks. So actually, this question is indeed some final exam. This is the only final exam question I still remember from previous years. Yeah, that's a payoff. All right, this is a payoff. S1, S2, S3. You got 3 stocks, and this is a payoff function, and you can try to find the price of this kind of payoff functions. The value, the price for these securities, and this is a payoff. S1 times S2 minus S1 times S3 positive part. Okay. And of course, you will see there are this kind of change of numerator techniques will first be applied here because you got S1 in common factor, so you want to bring this out. And then it just becomes S2 minus S3 positive part. So that's exchange option. That becomes exchange option. So you have a way to do that.
Can we use Markgraf's formula?
Yeah, you can. If you have this, you can. But I guess you still need to be careful about these parameters, which is what is R, what is sigma, because once you do change of numerator, it will be different, right? Some parameters there might be different. So you still need to be careful, but you can use any formulas you already learned, I guess. Yeah. So question 4. So question 4 is actually a very simple question once you understand what it's really about. Okay, you don't have to do very complicated calculations to find the answer, as long as you can understand it conceptually. Okay, so let's see what happening here. So it concerns about this foreign currency. So let's see, we live in Singapore. So let's say Singapore dollar is our domestic currency, and there is a foreign currency US dollar. So if I have $1 at the beginning, okay, so I have $1 at the beginning. So of course, the natural thing I can do about this $1 is I can put this $1 into a bank in US, right? So I put this $1 in a bank in US, then the bank will pay me interest rate. Ideally, it will pay me the interest rate at the risk-free interest rate in US. Because in US there is an interest rate, risk-free interest rate, but in Singapore it's a different number. Okay, so it will become an interest rate. I will get paid at this amount of interest rate. Okay, RF, which stands for the interest rate in US. So after some time, my US dollar deposit becomes e to power RF times t. Right, that's my interest accumulation. Okay, so that's what really happens in the ideal in this market. So how do we think of this US dollar? So in economics, when we have a currency and asset, they are quite different. Okay, but in our context, when we do financial math, they are basically the same. Okay, currency is just another type of asset. It's just another type of stock. Okay, so let's see. USD is just a code name for some stock. So at the beginning, I own 1 unit of such stock, USD stock. Okay, I have 1 unit of USD stock, and after some while, even though I did not do anything about that, it becomes e to power RF times RFT unit of stock, of USD stock. All right. At the beginning, I have 1 unit, but later I have e to power RFT unit. Okay, I did not do anything. I just put the stock there, and after some while, it becomes e to power RFT, e to power RFT unit. So what does that mean? It implies that actually, if you think of USD as a stock, then the stock is actually paying dividend. Okay, that explains why the number of units just grows automatically. Okay, the number of units I'm holding grows from 1 to this number. Why? Because this asset, this stock, pays me dividend, and I just reinvest all the dividend I receive to purchase more unit stocks, just like the stock, just like dividend-paying stock, as we discussed at the very, very beginning of the semester. Okay, so if you do not like this kind of notation, you can also think about what is the value of this kind of stock. So at the beginning, I have one unit of US dollar. That means I have X0 SG Singapore dollar. Okay, that's the exchange rate at the beginning. Okay, one USD equals to X0 SGD. So after some while, my US dollar becomes this number. So the total value of my portfolio in US dollar becomes e to power RFT times XT SG dollar. Okay, so if you think about this XT as some stock price, at the beginning, the stock price is X0, and I have 1 unit, and later the stock price becomes XT, and I have this amount of unit. So why? Why is the number of units expand automatically? And I'm not doing anything. That's because it implies that, or you could say, it is equivalent that this stock is pays me dividend at this dividend yield RF. All right. So ideally, it's just the dividend. The foreign interest rate can be regarded as the dividend yield if you look at the foreign currency as a stock. So to apply this idea here, so if you look at this FT, so FT is just the value of US dollar. Okay, that's foreign exchange rate. So FT. So under the domestic risk neutral probability QD, that means we are using our domestic currency as our numerator. Then the drift term of this FT under this risk neutral probability should be RD minus RF. Just like any dividend paying stock, the drift term will be R minus Q. So R should be interpreted as domestic interest rate, and the Q is equivalent to the foreign interest rate. All right? Agree? Okay. So yeah, so that's for F. So what about this S hat? So the meaning of S hat is stock price multiplied by this conversion rate. Okay. So S hat basically is the stock price in SG dollar, in Singapore dollar already. So let's say ST. ST itself is number, it indicates the let's say Microsoft stock price in US dollar. So once we convert it into Singapore dollar, then it has no difference with the new Microsoft stock trading in Singapore, which is counted in Singapore dollar. And stock price is just ST hat, right? So it's just a stock price. It's just a stock. ST hat is just a stock price, just like our typical stock, which is the drift term should be RD. Okay, drift term should be RD. It's just a typical stock. It's already in Singapore dollar, so we do not need to worry anything about that. So it's just RD. Moreover, if the Microsoft stock pays dividend at the dividend yield Q, what about this number? What about this drift term? The drift term actually should be RD minus Q. So for the dividend yield, actually in the original, in this Microsoft stock in US dollar, the dividend yield is always a proportional number. So Q itself does not concern any unit. It's not in US dollar or Singapore dollar. Q is always proportional. So when we calculate this, convert this stock price, actually the dividend yield will always be the same. We do not need to do any conversion related, but we do not need to do any adjustment about this dividend yield Q. This Q is the stock itself. It's about the stock itself. Okay, this Q, that's RD minus Q. So that's the drift term of ST hat. Okay, so that's the drift term of this number and this guy under this QD measure. Okay, so what happens if we are US person, if we live with American, then basically we'll see that 1 over F is just the stock, the stock name is SCD, and the stock paid dividend at the stock Singapore interest rate. So the drift term of this guy should be our foreign US interest rate minus Singapore interest rate. And ST itself is very it's just a very typical stock again. It's just a Microsoft stock. It's already in US dollar and we live in US, so it's just a risk-free interest rate in US. Sorry, it's in US, risk-free interest rate in US, and minus dividend yield. Okay, that's a typical stock. That's what we are most familiar with. Typical stock, the drift term should be R minus Q. Okay, and the foreign currency is you can just think of foreign currency as a different stock, as another stock, but the stock automatically generates yield, a dividend yield at this amount, at this rate. Okay, so that's the first two parts. I hope you can understand that. And once you can understand that, basically the following become very straightforward. So that So if you write, let's say, if you write down this dynamics on the QD measure, this is the domestic risk neutral probability, then immediately we will know this mu f. This number should be RD minus RF, right? This F stands for the US dollar, okay? Stands for foreign currency value. So it's RD minus RF. RF can be think sort of as an equivalent dividend yield of this US dollar. And what about this mu s? So basically, part C and part D helped us to pin down this mu s. So what do we do? How do we do that? The first thing we are going to do is to find out what is the drift term of this ST hat. So basically, that means we are going to apply ethos lemma to this ST hat. But what is ST hat? ST hat is ST times FT. Okay, ST hat is the stock value, stock price in Singapore dollar. So we need to convert the US dollar to Singapore dollar by multiplying this foreign exchange rate. Okay, so we apply ethos lemma to this guy, and we can find the drift term. And the drift term will be just like what we discussed previously. It should be RD minus Q. So after we apply ethos lemma, the drift term of this ST hat will become this number, these guys. And this guy should be nothing but RD minus Q, and this is implied by our argument before. Okay, our previous argument showed that this drift term must be RD minus Q. Since it's a stock, it's already in Singapore dollar, so it's R here, and the Q comes from its originally it's just paid proportional dividend yield. So this proportion is still be kept, will still be kept here, so it's minus Q, and we can equalize these two. And once we do that, and by realizing that mu f is RD, so mu f is RD minus RF, then basically you see we can solve mu s. Okay, this equation will give us an answer to what is mu s. So mu s is actually this guy. Okay, so that's mu s. And if you look at the PDE that we derived based on the hedging argument for this foreign currency problem. If there is no dividend Q, if Q is 0, that's RF minus this number. That will appear in this PDE. If you compare these results with the ones in your lecture notes. Okay, the PDE will always agree with the DT term in ethos lemma. Okay, and why we have that this real number comes from here, because the drift term of this stock price should be this number, should be this very weird number, and it comes from this whole argument here. Okay, so that's for question 4. Luckily, I still got time. So the last question is about this kind of option. So it's the fixed exchange rate foreign equity call. So there is a foreign stock containing foreign currency, and A will be our conversion rate. So that's still only one formula, only one theory basically, risk neutral valuation. Okay, so this is what we are going to do. This payoff function. Okay. Discount payoff under Q word. All right, this is the only thing we need to compute. Okay, to find out the price of this payoff, this call option. Okay, so immediately we find that A is actually a constant. So it does not relate it to our calculation rate about this expectation. So that's it. Right? So if you look at what's inside this expectation, it's just a European call option. Okay, that's just European call options. Okay, so let's try to apply Black-Scholes formula. Okay, but we need to do some modification. Why? Because if you look at the dynamic of this stock price, the dynamic is what? The dynamic is this guy. Remember, because we are doing this computation under this probability Q, so that the dynamic will be this number. It will become this guy. Okay? And what is mu s? We just find what is mu s. Mu s is some Rf minus Q minus some rho and I guess something like this. Okay? This is the mu s. Anyhow, this mu s is not. One way to do that is you could say equivalently this is some interest rate, or you could say it does not agree with the discount factor, because anyway this is a discount factor. I use D here, alright? I put a D here to indicate we are doing this under using domestic currency. Okay? So anyway, my point is, even though the discount factor here is the interest rate, the risk-free interest rate is RD, but if you look at the dynamic of ST under this probability QD, the drift term does not agree with the same, does not agree with this RD. It's a different number. Okay? So that in order to directly apply Black-Scholes formula, there are two ways. Either you could say that's because there are some dividend payment, equivalent dividend payment, so you need to make some adjust there. Or you could say this is actually just a number, so we need to add some equivalent discount factor. And anyhow, my point is you need to do some modification. It's not directly the same as Black-Scholes formula. You need to make some modification. But I'm sure you know how to do that. So anyway, it's just a log normal distribution, but you need to find out the meaning of the drift term should be consistent anyway. So if you do that, if you make this adjustment here, and you would end up with very similar results like Black-Scholes formula. But you need to be careful about what is D1 with D2, and maybe what is Anyhow, you need to make some adjustments. I guess you know what I mean, right? By making this kind of adjustment. Okay. So for the last few minutes, I just want to just summarize a little bit. So I guess you see, as you can see, no matter PDE, so there are two approaches, PDE or risk neutral pricing, but usually there are only one way we can test in exam, because PDE is so complicated. So usually risk neutral pricing. So once we come to risk neutral valuations, the formula, then it's just become the problem. Mathematically speaking, it's just a problem of how to compute the computation. Right? And anyway, this course is not exactly the basic probability course, so it really depends on how well you already learn about this probability. There are a lot of tricks you can try to apply there when you want to find the expectation of some pair of functions. Okay? So the trick we introduced in this module is change of linear. Okay? And also, a lot of exercises just give you some idea that sometimes we can make use of Black-Scholes formula if the pair of functions have the similar structure. We can always try to do some transformation so that we can directly apply some our existing results like Black-Scholes formulas or what kind of formula, all different kind of formula. Okay, but the most fundamental way is always integration. But that's just a very time-consuming. But it's always one of your choice. And other than that, I guess you really need to be flexible when you try to solve some new questions, new problems. You need to be flexible, and you may want to make some linkage between these new questions and to see whether you can do some transformation, do some reductions to transform the new problems to some old problems that you are more familiar with. Okay, so I guess that's my experience in solving mathematical problems. Okay. Try to reduce one difficult one to a less difficult one, and try to see whether you can use some any existing results you can to help you to find the answers. Anyway, I hope you can be prepared for the finals. And since I usually heard finals are much more difficult than midterm, so but just get relaxed. It's not that hard because. So anyway, so I would like to wish you good luck in your finals, not only in this module or any module to take this semester. So good luck with that, and also thank you for still sticking with me at the last week and last day of this semester. So thank you for that. So.